One of the instructional problems that I run into with this course is that most of the meaningful examples of what we're talking about are in higher dimensional space. It's very, very difficult to come up with something meaningful in 3 dimensions, which we can visualize, in order to help students understand what we're trying to do. This is my best attempt at that. I'm using a 3-dimensional example, and we're going to change the basis and reduce the dimension of the space. As I noted at the beginning of this day's lectures, the main purpose of this is for those big picture people who want to see where we're going. If the following example is difficult to follow, I would like you to try to see what's going on, but it may need time to marinate, and just be aware of that. It's going to start very simple, and then it's going to get a little twisted. Here, I have a very simple equation. It's the identity matrix times a vector is equal to that vector. Now, again, this is introducing a concept we talked about in the primer, which is just the very concept of an identity matrix. That's the matrix of all zeros with ones on the main diagonal. And when you multiply anything, whether this were a matrix, here it's just a vector, if you multiply anything times the identity matrix, the result is that thing. So the identity matrix is kind of like the number 1, the multiplicative identity. Anything times the identity is itself. All right, so now I'm going to take this matrix, very simple matrix formula, and I'm going to expand it out into a linear combination. Now, we see something familiar from the last video where I have coordinates times basis vectors. So whenever you have basis vectors, you want to think about those as axes for some coordinate space. Now, these vectors are not the entire axis. They're just the vector pointing in what we'd call the positive direction of that axis, right? Because the axis is an entire line. It's not just a little tiny vector of 1, 0, 0. It's the entire line. But those basis vectors are what determine the direction or the location of those axes. Here I have a point in space, point in 3-dimensional space. And I can think about that point as a vector, which is just the arrow from the origin to that point. Coordinates give us directions to that point along the basis vectors. So for any set of data points, the basis vectors are the same. So what we do is we compare the points by comparing their coordinates. None of this should be groundbreaking to you, but for instance here, x11 tells me how far I should go along that x direction. Typically call that the x, the y, and the z, so I'm going to use that here. The x21 tells me how far to go along maybe the y direction. And then the x31 tells me how far to go in the z direction. And these axes typically represent variables. So here I'm going to actually create some data, and I'm going to call axis 1 is length, axis 2 is weight, and axis 3 is width. And I'm going to label that point according to the coordinates that I just drew for it. Hopefully there's nothing confusing to this point. This is just a representation of plotting a data point in 3 dimensions. Now let's do a different point. Let's make it a blue point and give it new coordinates. And again, these coordinates tell me how far to go along each direction to reach the blue point. And from this picture, we would be able to conclude that when I compare the red and the blue point has a smaller length because its coordinate along the length axis is less. It has a smaller width, again, because it has a lesser coordinate, and a larger weight. Now, here's where we're going to turn this on its side a little bit, and we are going to change the basis. I'm going to do so by just rotating these axes a little bit. They will no longer represent length, weight, and width. And the points do not change. The points stay exactly where they were in space. It's these arbitrary axes. Now, you may not think of the axes as arbitrary. Previously, they were not. They were length, width, and weight. That's the source of our data. But now I'm kind of just drawing in some arbitrary axes here. I'm going to call them axis 1, axis 2, and axis 3. And I no longer have the previously listed point. Now I have wiggles. So this is the blue point, x12 wiggle, x22 wiggle, tilde, if you will. And these are new coordinates of those same points in this new basis that I've drawn. Now, the old axis didn't go away. The old axis is still there. Here, I'm going to draw it in gray. Okay, so length, width, and weight have not disappeared. They still exist in this space. I'm just ignoring them. I'm not using them. I want to use these new arrows. Why? Because, you know, I'm just that kind of first grader. I want to draw my own axes and create my own coordinate system. So again, these new coordinates tell us how far to go along axis 1, how far to go along axis 2, and they will, when I work all of that out, I will get the same original coordinates. Okay, just like in the previous video, we had the 2 examples for the elementary students and those representations were equal. The same thing will be true here. I can still get to the coordinates of the same points in that old basis. So I have these new coordinates that tell me, you know, how far to go along axis 1. So if I asked you, you know, which number is bigger, x tilde 1, 1 or x tilde 1, 2? I hope that even just looking at this picture, you could tell me that this red x tilde 1, 1 is bigger. Why? Because that point, I have to travel a larger magnitude along axis 1 than I do in this case. So, you know, I have these new basis vectors, but what do they mean, right? That's probably the first question that we ask. So let's move these expressions up to the top. And let's talk about these new axes for a minute. Let's kind of ignore the points and just talk about these new axes. Well, each axis is a linear combination of my original axes, right? I can get to axis 1 if I think about that as a vector rather than the whole line that spans the axis. If I think about it just as this direction vector, I can get to this vector from a linear combination of length, weight, and width. So just looking at axis 1 here, I'm going to give you these numbers. I'll tell you these numbers came out of my head and with a little help from a computer. These are not numbers that you would have to come up with on your own. They will always be given to you. Okay, but the computer tells me this axis I picked is 0.89 times length minus 0.09 times weight. Again, this is a 3-dimensional drawing. It's probably a little hard for you to realize that that went behind the slide. And 0.4, oops, I went the wrong way in my, sorry about this. So 0.89 times length minus 0.09 times length and 0.45 times width. that linear combination of my original axes will give me that new axis. I can do the same for the other axes, but first let's take a harder look at this axis 1. It tells me that it's 0.89 times length, it's 0.45 times width, and just a little bit of some negative number times weight. So there's really two things that are factoring in largely to this axis, and it's length and width. That weight has such a small contribution to this axis that for now, just for convenience sake, we're gonna almost ignore it and think that weight has very little contribution. And so axis 1 basically kind of represents size, because it lines up much more with length and width than it does with weight. Another way to think about that is that as a point increases their weight, their coordinate along axis 1 doesn't really change very much. The next is axis 2. So axis 2 is 0.27 times length plus 0.89 times weight. So a very small amount, and then a large amount for weight, and a relatively small amount for width. And so you might say that axis 2 predominantly represents weight. Sure, length and width are contributions to this axis, but weight is really what's driving this axis, or weight is the thing that's most related to this axis. Again, these concepts will become much clearer as we talk more and more about this. I just want to try to give you an example of everything right now. So I have axis 1 and axis 2, and let's just say I'm going to ignore axis 3 for now. I just don't feel like dealing with it. So bye-bye. What that essentially means, though, is that I just change these coordinates corresponding to axis 3. I'll just change them all to 0. And then, they'll go away. They will move out of my life forever. Okay, so now I don't have axis 3 anymore. I just have axis 1 and axis 2. And bringing this top expression down into focus now, and removing those last 3 coordinates, I have some coordinates along axis 1, which represents size, some coordinates along axis 2, which represents weight. And I'm going to delete the old axes from my picture. And now I have this picture. This is a right angle, by the way. You can't see that necessarily just because of the way it was drawn, right? But let's flip this around into something I'm more used to looking at, right? Let's just rotate this around so that I take that subspace. Here's where I get to that subspace that I kind of pluck out of its original space and lay in front of me so I can look at it nice and neat. I have axis 1 and axis 2. I have my red point, I have my blue point. And I might want to draw some conclusions here. I'll go ahead and put size along axis 1 and weight along axis 2. And I can draw some conclusions here that in order to get to the blue point, the red point, approximately I go the x1 wiggle along axis 2, x2 wiggle along axis, I think I said axis 2, axis 1, axis 2. Okay, again, this is just a new coordinate representation. And from this, I will infer that the red point has a larger size and a smaller weight relative to the blue point, because its coordinate along this axis, which we're deeming size, is larger, and its coordinate along axis 2 is smaller. Okay, we can do the same thing for the blue point, kind of draw out its coordinates along these new basis vectors. Now, one mistake I have in this slide is that I have an equals here. Since we dropped out those third coordinates and we just arbitrarily set them to 0, this is not an equals. This is an approximately equal. Okay, so in this example, we'll go ahead and use the terminology, I've reduced the dimensions of the space, and just by doing so, I've approximated my data. Okay, and so the blue point has a small size and a large weight relative to the red point, of course. So I want to just introduce some terminology here. We will revisit this terminology several times over the next several lectures. Using this example, these new axes that I draw tend to be called factors. These are factors, latent factors that I've uncovered in my analysis. The entries in those factors are typically called loadings. They tell you how each of your original variables relates to your new factor. The coordinates in our new basis are typically called scores. Sometimes some packages will just refer to them as coordinates, but more often you'll see them in the literature called scores. In the next video, I'll walk through a more complete example which shows how this is done through matrix factorization.